Hi, my name is Andrea Spurck. I'm a master's student at Ohio State University with Dr. Bob Gates, and I'm going to present some of my master's research on modeling changing winter duck distribution in the Great Lakes region. My first chapter assessed historical Christmas bird count data from 1966 to 2021 to model the changes in duck relative abundance in the Upper Mississippi and Great Lakes Joint Venture region. My second chapter involved predicting future winter duck relative abundance based on climate change projections under different emissions scenarios. Since most of us are familiar with the impacts of climate change, I'm just going to give a brief introduction with how it relates to winter duck distribution. Previous research has indicated a northward shift in winter duck distribution. The map of the eastern United States shows the annual percent change of duck abundance increasing more in northern latitudes and decreasing slightly in southern latitudes. This winter range shift in duck distribution could increase foraging pressure in areas that historically did not support this greater abundance of overwintering ducks. There is also concern for migration mismatch with the timing of resources and creating ecological traps. As climate change continues, studies predict that reduced ice cover and warmer temperatures could increase lake effect snow and extreme weather events. As ducks begin overwintering at northern latitudes, the extreme weather events could result in additional mortality, especially for species with specialized foraging strategies. From a management perspective, differences can also occur between peak duck abundance and the timing of waterfowl hunting seasons and viewing opportunities. I used historical Christmas bird count data for 17 dabbling and diving duck species from 1966 to 2021. Models were created for different groups of species, including mallards and American black ducks, which are a larger bodied generalist species that can utilize different food resources such as agricultural fields and can endure colder temperatures unless snow cover prevents food access. Another group consisted of wetland obligates, which are species that have specialized foraging strategies and require access to open wetlands for feeding on vegetation and invertebrates. I grouped 5 wetland obligates that included northern pintail, green-winged teal, American widgeon, gadwall, and northern shoveler. 8 diving ducks were also used in the analysis, but for the purposes of this presentation and the time restraints, I'll just be focusing on the generalist dabbling ducks and wetland obligate dabbling ducks. Most previous research has been conducted at a larger geographic scale, but regional differences might not be detected at this scale. I focused on the Great Lakes region since this area provides important mid-latitude stopover sites for migrating waterfowl in the Mississippi Flyway. There are also complex climate change interactions regarding the Great Lakes. The study area consists of the Upper Mississippi and Great Lakes Joint Venture region, which includes the main bird conservation regions of 12, 23, and 22. This area was overlaid with 100 by 100 kilometer grid cells, with the pink cells in this figure representing the joint venture boundary extent. I gathered Christmas bird count data from 1966 to 2021 that included more than 25 million mallards and American black ducks and more than 700,000 wetland obligates. There was an average of 3 surveys per 100 by 100 kilometer grid cell. Post hoc analyses were conducted using the Christmas bird count trends and Weather Severity Index values. Weather Severity Index calculations involved adding the inverse of average temperature, days with temperature at or below freezing, plus average snowfall, plus days with snowfall at or above 2.54 centimeters. All 168 grid cells had an associated WSI value, with lower values being milder winter weather and higher values being more severe winter weather. Bayesian hierarchical models were used due to the spatial and temporal autocorrelation, which runs based on the connections between each grid cell. I used the R-inlet package to run these models. The post hoc analyses assess the interactions between the Christmas bird count trends with the weather severity indices, latitude, and wetland cover. This is some example code for the inland models that provided values of percent change per year, survey effort, and relative abundance for each grid cell based on the spatially weighted structure from the connectivity of the neighboring cells. There is also a 95% credible interval established for these values. The tau value maps show the percent change per year. Mallards and American black ducks did not have as notable of a pattern as I was predicting. There were generally some darker red grid cells in the northwestern region of the joint venture, which indicates higher percent change per year, but overall the values were fairly scattered throughout the area. On the other hand, the map of the wetland obligates shows increasing percent change per year values across the entire joint venture region. There were specifically some higher percent change values in Iowa and Missouri, which were along the Mississippi River. There were also areas in Minnesota and northern Wisconsin that had mallards and American black ducks present, but did not have any of the 5 wetland obligates detected during the Christmas bird count surveys, which suggests that these areas have winters that are still too harsh to support wetland obligates. I ran post hoc analyses for latitude, weather severity index values, and wetland cover. Mallards and American black ducks had a weak positive trend between percent change per year and WSI values, with greater increases in areas that historically had more severe winter weather. Wetland obligates had a strong negative relationship with percent change per year and WSI, as more severe winter weather reduced the percent change per year. These associations with WSI were above 0 for the wetland obligates until a certain point, which indicated that these species were not consistently increasing in cells that historically had more severe winter weather. Chapter 2 of my thesis involved using climate change models to predict changes in winter duck abundance based on different emission scenarios for mid and late 21st century. I created models for 2050 and 2100 with emission scenarios B1, which represents less extreme temperature increases, and A2, which represents more extreme temperature increases. The figure shows the change in WSI values that we have already seen between 1966 and 2021, with greater shifts towards milder winter weather in Minnesota, Wisconsin, and Michigan. I modeled future WSI values based on the historical WSI tau linear regression in Chapter 1. This resulted in an annual percent change that was influenced by the WSI gradient, as seen in this figure that shows the wetland obligate annual percent change for emission scenario A2 in 2100. I then calculated estimates for future count data based on the WSI tau relationship and recent Christmas bird count data, which provided a better assessment of the future predictions. For this presentation, I focused on emission scenario A2 since previous studies have indicated that these climate change models tend to underestimate the shift towards warmer winter temperatures. For mallards and American black ducks, future projections suggest similar increases in annual percent change, except for 2100 A2 emission scenario. Grid cells with lower WSI values between -9 and 7 had a small decrease in annual percent change of around -1%, and grid cells with the most severe WSI value of 45 had a 5% annual increase. Estimated counts for A2 in 2100 showed more increases in the western, upper Mississippi, and Great Lakes joint venture region. Based on all climate change emission scenarios, wetland obligates were expected to move into northern grid cells that historically established a WSI threshold. Milder WSI values of -10 to 0 had a 2.5 to 5% annual increase, and the most severe WSI value of 45 had an annual increase of 15.5%. Winter weather patterns in Minnesota and Wisconsin were mild enough to support wetland obligates, and there were greater increases in areas that had more severe WSI values. Many of these increases occurred near larger bodies of water such as the Mississippi River and Great Lakes. As expected, duck species had different responses to climate change. Wetland obligate dabbling duck abundance was increasing in northern latitudes, but it depended on a certain threshold of severe winter weather. Historically, these ducks were unable to occupy Minnesota and northern Wisconsin, but it was predicted that future increases in winter temperature could shift the threshold, so wetland obligates could overwinter at these northern latitudes. There are also more increases near larger bodies of water. Mallards and American black ducks were increasing at northern latitudes in areas with historically more severe winter weather. Future predictions indicated that mallards and American black ducks would be increasing more in the western joint venture region. It is important to work towards understanding shifts in winter duck abundance from climate change. From a management perspective, it'll be important to provide additional habitat and resources to support the extra abundance of overwintering ducks in the Great Lakes region. Historically, northern latitudes did not support this greater abundance of overwintering ducks, which could have impacts on other wetland-dependent species as well. There were larger increases in the western upper Mississippi and Great Lakes joint venture region, especially near larger bodies of water, so it'll likely be important for management to focus on these areas. Additionally, as the frequency of unpredictable extreme weather events is expected to increase, providing ample food resources will be necessary for overwintering ducks. These shifts in duck migration patterns will have impacts on hunting and wildlife viewing opportunities, but this is variable each year and is overall more noticeable at smaller regional scales. Thank you for your time with listening to my presentation. I also want to thank the Terrestrial Wildlife Ecology Lab at Ohio State, the Ohio Division of Wildlife, Waterfowl Research Foundation, and Winus Point Marsh Conservancy. Please let me know if you have any questions.